The Milky Way, a city of stars, of which we're the inhabitants. We've seen a gorgeous picture of the Milky Way taken from Death Valley, under the truly dark skies out in the western desert, with a fisheye lens so it appears to wrap around the sky. As viewed from a dark site, of which there are many in Arizona, it girdles the sky and of course continues in the southern hemisphere. Some of the best views of the Milky Way come from the southern hemisphere, where the galactic center passes almost directly overhead. Observations over a series of decades have mapped out our position and the size and shape of the Milky Way galaxy. The disk of stars, in which we are a part, is 100,000 light years in diameter and about 1,000 light years thick. There's a pileup of stars in the center of the galaxy called the bulge. The disk contains many young and blue stars, regions of star formation and patches of gas and dust and obscuring material, and ragged spiral arms. The spiral arms, as you might expect, trailing the direction of rotation of the galaxy. Towards the center of the galaxy from our position, there's a pileup of stars called the bulge, like two fried eggs back to back. The stars are mostly older and red or yellow in color. We're 28,000 light years from the galactic center. In addition, there's a third, more diffuse component that's nearly spherical in shape, extending far above and below the disk and beyond it. Although it's hard to see, it actually contains most of the mass of the galaxy, often in the form of old stars, but also occasional giant clusters of stars, 100,000 strong, called globular clusters. Astronomers have distinguished two general populations of stars in our galaxy and all others. They're numbered historically and have no other reason for their naming, but population 1, or the disk population, are younger stars mixed in with gas and dust from which they form and left over from their formation, and typical of young and open and ragged clusters like the Pleiades, visible in the night sky to the naked eye. The halo, or population 2, is a pristine population without gas and dust of essentially old stars, redder, often lower mass, and this is where the globular clusters exist, most of which are more than a few billion years old. There's also a mixed population in the bulge of population 1 and 2, some younger blue stars and older red stars. The space between stars, called the Interstellar Medium, is not entirely empty, but it's far better than the best vacuum on Earth. With roughly 1 atom per cubic centimeter, it's a billion times more rarefied than the air we breathe. It's made of 90% gas and 10% dust. The gas, like most cosmic compositions, is mostly hydrogen and helium, and the dust consists of tiny, submicron-sized particles, either of almost pure soot and carbon material, or silicates, the basis of rock. Although this thin gruel of material is almost invisible to the eye, viewed over long path lengths through the galaxy, it has an impact on distant light, both reddening and extinguishing that light. In fact, before interstellar dust was recognized in the 1920s and 1930s, people thought that the galaxy was far smaller than it is. In geography, it turns out we occupy a local bubble. The density of stars near the Sun is relatively low because we're 2/3 the way out in the spiral disk. But in terms of gas and material, it's even more rarefied. It appears that there's a local region where multiple supernova events have left overlapping bubbles, evacuating the region with their blast waves, thousands or even tens of thousands of years ago. Evidence of this comes from X-ray emission, where we find that our region is less dense, but also 100 times hotter than normal material in the interstellar medium. Radio telescopes were used in the 1930s and 40s to map out the disk of the galaxy. Because of the effects of dust, when we look through the disk, especially towards a galactic center, it's like looking through a closed door. Visible light does not penetrate the 28,000 light years to the galactic center. In fact, it's hard to see more than a few thousand light years in any direction. But radio waves penetrate completely across the galaxy and allow us to measure Doppler effects of gas and so map out the rotation, which is a circular pattern of speeds. Knowledge of the Milky Way has grown as we've opened up the electromagnetic spectrum to astronomical observation. The classical view of the Milky Way, showing this ragged pattern of bright patches and dark patches, is a function of the dust within the disk of our galaxy. Moving to longer infrared wavelengths, the clear and thin disk, just 1,000 light years thick, is much more easily visible. The longest wavelengths, radio waves and far infrared wavelengths, show where the coolest dust is, and also some of the energetic phenomena associated with the late stages of supernova evolution. X-rays, by contrast, find the very hottest gas, or the most energetic phenomena, such as binary stars, where gas is accelerated to very high temperatures. Also, very young binary pairs and very massive stars are visible in X-ray emission. The full panchromatic view of the Milky Way across the electromagnetic spectrum tells us something different about the Milky Way in every wavelength regime. Our system of stars, the Milky Way, is a spiral galaxy consisting of roughly 400 billion stars. The vast majority of those are faint red and white dwarfs. It has three components: the disk, where we sit 2/3 of the way out from the center, almost 30,000 light years from the galactic center, a bulge, or a pileup of older and redder stars towards the center of the galaxy, and a much larger and more diffuse and nearly spherical halo of stars that nonetheless contains most of the mass of the galaxy. Mapping out the galaxy and learning its behavior requires observations across the electromagnetic spectrum.